In a conventional rocket engine, engineers try to keep the flame stable. Inside this machine, they deliberately create a supersonic detonation wave and let it continuously race around the combustion chamber. The wave does not travel straight toward the nozzle. It moves circumferentially through an annular channel, while fresh propellant enters and combustion products leave mainly in the axial direction. A small mismatch can leave propellant incompletely burned, force hot gas backward through the injector, or heat the chamber wall beyond its material limits. Yet if the rotating wave remains stable, detonative combustion can create a pressure rise that conventional deflagrative combustion does not exploit in the same way. How can an engine continuously feed a detonation without being destroyed by it? And where does the extra pressure actually become useful thrust? An RDRE still has familiar parts. Propellant lines, an injector, a chamber, cooling passages, and a nozzle. The difference lies in chamber geometry and flame propagation. Instead of one broad open volume, the reaction zone is commonly an annular channel between an inner body and an outer wall. Fuel and oxidizer enter through a ring of injector elements at the head end, forming a fresh mixture layer around the circumference. In a conventional engine, a deflagration front moves subsonically relative to the unburned mixture. The flame itself is not a shock wave. A detonation is different. A leading shock compresses the unburned mixture, while rapid reactions immediately behind it release energy and sustain a coupled structure traveling supersonically. In an RDRE, that structure is not allowed to run down the chamber and disappear. The annular geometry gives it a closed path. One or more waves can continuously circle the chamber, nearly perpendicular to the average propellant flow direction. After the wave passes a location, high-pressure combustion products expand toward the chamber, exit, and nozzle. Pressure near the injector then falls. Fresh propellant moves back into the channel and rebuilds an unburned layer behind the wave. When the wave completes another circuit, it encounters the layer that has just been replenished. The entire mechanism depends on a race. The injector must rebuild the propellant layer before the detonation wave returns. The first enemy appears as soon as the detonation sweeps past the injector face. Pressure behind the wave rises abruptly. For an instant, that pressure difference tries to push combustion products backward into the propellant passages. Enough injector pressure drop can resist backflow and help forward flow recover. But the feed system must work harder. So part of the detonation cycle's pressure advantage can be spent at the injector. The second enemy is mixing. If fuel and oxidizer are not sufficiently uniform, some propellant may burn slowly behind the wave instead of joining the detonation. Wave speed and strength can fall, while pressure gain potential is lost to deflagrative burning. The fresh layer cannot have an arbitrary height. If it is too shallow, the wave may fail to sustain itself. If it is too deep, some mixture may move axially out of the chamber before the wave arrives. The number of rotating waves also changes the refill time available at each location. Then comes heat. The chamber does not merely see hot gas. A pressure peak and reaction zone repeatedly sweep close to its walls at roughly 1 to 2 kilometers per second in representative operating modes. Heat load varies with axial position, circumferential position, and wave mode. Hardware that survives a few seconds may not survive for minutes. How can the injector resist reverse flow and mix rapidly without consuming the pressure advantage, while an extremely short chamber survives the thermal load? The answer does not sit in one component. It lies in the way the complete flow loop is coupled. Start with the injector. Each passage is designed to favor forward flow over reverse flow, a behavior often described as injector diadicity. This is not a slow mechanical check valve. Passage geometry, area, jet interaction, and the inertia of the propellant columns must resist backflow in an extremely rapid pressure oscillation environment. After chamber pressure drops, injection must recover almost immediately. Fuel and oxidizer enter the gap mix and build the required layer before the next sweep, without leaving too much propellant to burn slowly. Next comes the annular geometry. A channel that is too narrow raises the wall area to volume ratio and intensifies heat loading. A channel that is too wide can make the wave structure harder to control. Diameter, chamber length, and throat area jointly influence average pressure, product expansion, and the number of waves that can persist. The thermodynamic opportunity begins at the detonation front. The shock compresses the mixture before chemical energy is released, producing a high-pressure product region. This places the RDRE in the family of pressure gain combustion devices. But chamber flow varies sharply in time and around the circumference. To determine whether the engine truly benefits, engineers must evaluate total pressure, thrust, propellant flow, and every loss in the feed system and nozzle. The high-pressure products expand axially through the nozzle, converting enthalpy and pressure into exhaust velocity. If the exit flow is too non-uniform, the nozzle is poorly matched, or the injector consumes too much pressure, the advantage created at the wave front can shrink. Cooling operates at the same time. Cold propellant passes through channels integrated into the chamber wall and absorbs heat before reaching the injector. In NASA hardware, high-conductivity GR-COP42, copper alloy, and additive manufacturing allow complex cooling passages to be placed close to high heat load regions. Wall survival still depends on temperature, thermal gradients, cyclic pressure, and fatigue life. Wave sustenance is therefore a physical feedback loop. The wave creates pressure, injection is briefly suppressed, products expand, injection recovers, a fresh layer forms, and the wave returns. The complete engine can now be followed as one continuous process. In the in-row-D's configuration, pumps deliver liquid methane and liquid oxygen to the thrust chamber assembly. Propellant absorbs heat through regenerative cooling passages, then passes through the injector ring, and forms a mixture layer in the annular channel. A detonation front sweeps across that layer. The mixture is compressed and reacts within the coupled wave structure. Behind the front, high-pressure gas expands axially. As the wave moves on, pressure near the injector falls, the propellant jets recover, and the next fresh layer begins to form. Around the circumference, different regions coexist. One has just detonated, another is expanding, another is refilling, and another is about to be swept. The nozzle receives the combined output of all those regions and accelerates it to create thrust. NASA has demonstrated regeneratively cooled RDRE hardware in extended ground firings. A test announced in 2023 ran for 251 seconds and produced more than 5,800 pounds force of thrust. The later in-row-D's program developed a pump-fed liquid methane and liquid oxygen system in the 10,000 pound force class. Its thrust chamber assembly fired for more than 340 seconds in 2025. Those milestones show sustained operation in large hardware, not readiness to replace every rocket engine. Operability, service life, system-level benefit, and mission-relevant testing still have to be demonstrated. A rotating detonation rocket engine does not hold an explosion stationary. It gives a detonation wave an annular raceway where it repeatedly consumes a freshly rebuilt propellant layer, while combustion products expand axially toward the nozzle. The injector resists backflow without giving away too much pressure. Chamber geometry supports the desired wave mode. Regenerative cooling protects the walls. The nozzle converts a highly non-uniform pressure field into useful thrust. The revolutionary step is not simply creating a detonation. It is synchronizing a supersonic wave with propellant flow, heat transfer, and pressure closely enough to turn a normally destructive phenomenon into a continuous engine cycle.